A thin ribbon of grey clay slices through the rock. It is no thicker than a coin. It sits quietly between two massive chapters of Earth's history. Below lies the Cretaceous period, packed with the fossilized remnants of a vibrant world. Above lies the Paleocene, a landscape of biological silence. This tiny layer of sediment holds the physical mechanism of an apocalypse. We need to know what is inside, to read the chemistry of the past. We must destroy a piece of it. Gloved hands carefully scrape a sample of the grey boundary clay from the rock face. It is brought back to the lab. The sample is placed into an agate mortar and crushed with a pestle. The solid rock breaks down into a fine, pale powder. This powder is dissolved and fed into a mass spectrometer, a machine designed to weigh individual atoms. The machine fires a beam of ions at the sample, sorting the resulting fragments by their mass and charge. We are looking for anomalies. We are looking for an element that does not belong in the standard crust of the Earth. The data returns a massive, unmistakable spike. The instrument registers concentrations of a heavy metal called iridium. Iridium is exceptionally rare on the surface of our planet. Most of it sank to the Earth's core during planetary formation. But it is abundant in space. It is a common ingredient in meteorites and asteroids. Finding a dense, global layer of iridium right at the exact moment the dinosaurs disappear provides a physical chain of custody. It points to a singular, catastrophic trigger. SRC-01, Journal article. 1980, Late Cretaceous, about 66 million years ago. Reconstruction begins with a blinding flash. A rock from space, roughly 10 kilometers across, strikes the shallow waters of the Chicxulub crater. The impact releases energy on a scale that defies standard measurement. The bedrock vaporizes instantly. A plume of molten rock, sulfur, and dust is ejected high into the atmosphere, wrapping the entire globe in a choking shroud. The dinosaurian monopoly ends in an afternoon. The heat pulse is only the beginning. The real killer is the darkness. Billions of tons of soot and sulfur aerosols block the sun. Global temperatures plummet. Without sunlight, the engine of the global food web grinds to a halt. Photosynthesis stops. The broad-leafed trees and towering conifers wither and die. The giant herbivores that rely on vast quantities of fresh vegetation starve. The apex carnivores that hunt the herbivores soon follow. It is a total ecological collapse. SRC-01, Journal article. 1980, Present day, Palynology slide prep. We can trace the immediate aftermath of this collapse by looking at microscopic fossils. In a sterile lab, technicians place small chunks of Paleocene sedimentary rock into plastic beakers. They add hydrofluoric acid. This acid is highly dangerous. It dissolves the silicate minerals of the rock entirely, leaving behind only the toughest organic material. The resulting residue is washed, centrifuged, and mounted onto a thin glass slide. We place it under a microscope. The view through the lens reveals a graveyard of spores and pollen. In the layers immediately following the impact, the diverse pollen grains of flowering plants and ancient trees vanish. In their place, a single type of microfossil completely dominates the slide. We find an overwhelming abundance of fern spores. This phenomenon is known as the fern spike. It is nature's green flag of recovery. Ferns are pioneer plants, uniquely adapted to colonize devastated, nutrient-poor landscapes. They do not need rich soil or stable climates to take root. They thrive in the ruin. Early Paleocene, about 65 million years ago. Reconstruction of this early recovery world reveals a landscape of shadows and ferns. It is cold. The air is still thick with residual dust. And the silence is profound. The giant terrestrial ecosystems have been erased. But if we look away from the dead forests and peer into the slow-moving rivers, we find survivors. Beneath the murky surface, a medium-sized reptile waits. This is Bretesuchus. It is a semi-aquatic crocodiliform, measuring about 3 meters long. Its body is covered in tough scales. Its jaws are lined with sharp, conical teeth built for gripping slippery prey. Borealoschus lies completely still in the cold water. It waits in the dark. It is a survivor of the apocalypse. SRC 05, Journal article. 1997. The survival of Borealoschus exposes a critical rule of mass extinctions. Survival is rarely about being the smartest or the strongest. It is about your energy budget. Borealoschus is cold-blooded, meaning it draws its body heat from the environment. When the impact winter hits, it can simply slow its metabolism down to a crawl. It can go months, perhaps over a year, without a substantial meal. Furthermore, its environment protects it. The rivers act as a thermal buffer against the extreme temperature swings happening on the land above. Present day, ecological diagram. We map exactly why the rivers became sanctuaries. An ecological diagram of the Cretaceous period shows two distinct food webs. The first is the terrestrial sunlight web. Plants turn sunlight into food. Herbivores eat the plants, and carnivores eat the herbivores. When the Chicxulub crater event blocked the sun, this entire chain shattered from the bottom up. The second is the detritus web, found in rivers and lakes. This web does not rely on living plants. It relies on dead organic matter washing into the water, feeding bacteria, insects, and small fish. When the forests died and washed into the rivers, the detritus web actually experienced a massive influx of fuel. Borealoschus survived because it belonged to a food chain fueled by death. SRC 05, Journal article. 1997. We can't tell the exact day the dinosaurs died from this evidence. What it does support is a sudden, massive injection of extraterrestrial material that fundamentally broke the sunlight-dependent world. The impact acted as an absolute biological filter. It stripped away the giants. It left the Earth to the small, the adaptable, and the scavengers. The ecological slate was wiped clean. As the dust slowly settles and the sun begins to pierce the clouds once more, the survivors find themselves in an empty world. The vacuum is vast. The race to fill the apex niches is about to begin. We look at a map of the Earth as it existed roughly 60 million years ago. The familiar continents are recognizable, but their arrangement is fractured. In the north, North America and Europe are still largely connected, forming a vast, shared landmass. But as our gaze moves south, we see a different reality. The ancient supercontinent of Gondwana has broken apart. South America is entirely isolated. It is an island continent, cut off by deep ocean trenches from the rest of the world. Isolation breeds evolutionary strange loops. Without the constant pressure of migrating competitors, the surviving animals on this island continent are free to experiment. They can push their body plans to the absolute limit. And as the Earth recovers from the impact winter, the climate undergoes a radical shift. The cold darkness fades. A massive spike in atmospheric carbon dioxide traps the sun's heat. The world transforms into a sweltering, humid greenhouse. The tropics begin to expand outward, pushing toward the poles. Middle Paleocene, about 60 million years ago, reconstruction of this greenhouse island reveals an ecosystem where reptiles rule. A creature emerges from the dense, steaming undergrowth. This is Bretesuchus bonaparte. It is a crocodilomorph, but it has completely abandoned the rivers that sheltered its ancestors. Bretesuchus stands high off the ground on long, muscular legs. It is built for sustained movement on solid earth. Its snout is deep and narrow, lacking the broad, flat crushing power of modern crocodiles. We infer it is an apex predator because of its teeth. The fossilized jaws of Bretesuchus are lined with zyphodont dentition. These teeth are compressed, curved, and heavily serrated along the edges, much like a steak knife. This is the exact same tooth morphology found in the predatory theropod dinosaurs that vanished just a few million years prior. Based on tooth wear patterns, A conservative interpretation is that Bretesuchus used a swift, slicing motion to shred the flesh of early mammals and smaller reptiles. In the absence of dinosaurs, the crocodilians simply stepped out of the water to reclaim the land. SRC04, Journal article. 1993, present day, Cerrejón coal mine. To understand just how extreme this Paleocene greenhouse became, we have to look deeper into the tropics. Heavy machinery roars under the equatorial sun. We are in the Cerrejón open-pit coal mine in northern Colombia. The scale of the excavation is staggering. The terraced walls of the mine cut hundreds of meters down into the earth. They expose thick layers of gray shale sandwiched between massive seams of coal. These coal seams are the compressed remains of the very first neotropical rainforests. Surveyors walk across a newly exposed section of shale, placing physical scale bars next to a series of fossils. They are mapping a cluster of vertebrae. But these bones are wrong. They are far too large. A paleontologist brushes away the gray dust, revealing the distinct T-shaped neural spines characteristic of a snake. The team applies plaster jackets to the massive bones to prevent them from fracturing as they dry in the sun. The sheer size of the jacket required hints at an animal that defies biological logic. SRC02, Journal article. 2009, present day, vertebral scaling models. Back in the morphology lab, we place one of the fossil vertebrae on a digital photogrammetry turntable. As it spins, a laser scans the surface, creating a highly precise 3D model. We pull up a digital scan of a vertebra from the largest modern green anaconda, an animal that can reach over 5 meters in length. On the screen, we nest the anaconda vertebra inside the digital ghost of the fossil. The Paleocene bone dwarfs it entirely. The width of a snake's vertebra roughly dictates the width of its body. By applying volumetric scaling mathematics, we extrapolate the total length of the animal. The numbers lock in. We are looking at a snake that stretched between 12.8 and 14.3 meters long. It was roughly the length of a standard city bus. Its mass is estimated on the order of 1.000 kilograms. This is Titanoboa cherrygenensis. SRC02, Journal article. 2009, Middle Paleocene, about 60 million years ago. Reconstruction, Titanoboa glides silently through a slow-moving, murky river system. The dense canopy above blocks much of the light, casting long shadows across the water. The snake's massive, barrel-shaped body displaces the water with slow, powerful undulations. It is a non-venomous constrictor, closely related to modern boas, based on the sharp, recurved teeth found in a rare skull fragment. It likely ambushed massive prehistoric fish, overpowering them with sheer muscular compression. But Titanoboa is more than just a predator. It is a biological thermometer. Because snakes are cold-blooded, their maximum potential body size is strongly influenced by the ambient temperature of their environment. They cannot generate enough internal heat to sustain a massive body plan in cool climates. By running the metabolic scaling models backward, one study argues this size requires a mean annual neotropical temperature of 32 to 33 degrees Celsius. This suggests the Paleocene tropics were vastly hotter than anything experienced today. SRC02, Journal article. 2009. We can't tell exact maximum environmental temperatures from this evidence alone. What it does support is a reptilian metabolism functioning in a super-greenhouse world. Some climate models struggle to reconcile these high temperatures. The constraints of this scaling remain debated. It is possible that the sheer lack of large competitors, ecological release, also allowed Titanoboa to push past normal biological limits. The island of South America proves that when the dinosaurs disappeared, life didn't pause. The reptiles simply scaled up. They took the apex niches on land and in the water, perfectly adapted to the sweltering heat. But this extreme reptilian dominance was a localized experiment. If we want to know what happened to the mammals, we have to travel north. we must look at the connected continents of Laurasia. We reset our view of the globe, focusing on the northern hemisphere. The map shows North America and Europe locked together in a massive continuous landmass known as Laurasia. A temporary land bridge spans the North Atlantic, allowing flora and fauna to wander freely between the two continents. This interconnected world is a completely different evolutionary theater than the isolated island of South America. For over a century, the story of this northern world was written as a simple narrative of mammalian triumph. Textbooks claim that once the non-avian dinosaurs vanished, our small, furry ancestors immediately inherited the Earth, rapidly diversifying to claim the top of the food chain. But the fossil record of the Paleocene tells a much darker, more complicated story. The mammals were not alone. Late Paleocene, about 56 million years ago, reconstruction, a massive shadow falls across the dense, humid forest floor. A creature steps out from the ferns, standing over 2 meters tall. It is a bird, but it lacks the grace of flight. Its wings are reduced to useless, vestigial nubs. It walks on thick, heavily muscled legs, and its skull is enormous, nearly the size of a horse's head. This is Gastornis. For decades, paleontologists viewed Gastornis and its North American cousin, Diatrema, as the ultimate terror birds. Museum dioramas depicted them as ruthless, apex predators. They were shown using their massive beaks to hunt down and crush the primitive, dog-sized ancestors of modern horses. The narrative was simple: mammals survived the asteroid, only to spend the next 10 million years living in fear of giant, terrestrial birds. We assumed that the dinosaurs hadn't really given up control of the land, they had just grown feathers. Present-day, isotope prep lab. To test this terrifying assumption, we must look closer at the chemistry of the bones. In a specialized prep lab, a technician secures a small fragment of fossilized Gastornis bone under a microscope, using a high-speed Dremel tool fitted with a tiny diamond drill bit. They carefully grind away a millimeter of the fossil surface. The destructive sampling creates a tiny pile of fine bone dust. We need this powder to read the isotopic signature locked inside the calcium. Animals build their bones using the calcium from their food. Calcium comes in different molecular weights, or isotopes, such as calcium-44 and calcium-42. Every time an animal eats a plant, its body slightly favors the lighter isotope. When a carnivore eats that herbivore, the ratio shifts again. By measuring the exact ratio of these calcium isotopes in a mass spectrometer, we can determine an animal's trophic level. We can determine who was eating whom. SRC03, Journal Article, 2014, Present-day, calcium isotope results. We plot the resulting data onto a graph. The y-axis represents the ratio of heavier to lighter calcium isotopes. We plot the known values for famous predators. Like the carnivorous theropod dinosaurs, they cluster tightly at the top of the graph. We plot the known values for herbivorous dinosaurs and early grazing mammals, and they cluster at the bottom. We take the data point for Gastornis and plot it on the graph. It does not land anywhere near the carnivores. It drops straight down, aligning perfectly with the known herbivores. The midpoint reframe is absolute. Gastornis was not hunting early horses. It was eating leaves. The entire concept of the terror bird in the Paleocene Northern Hemisphere was a myth based on the intimidating size of its skull. SRC03, Journal Article, 2014, Late Paleocene, about 56 million years ago, reconstruction, the true nature of Gastornis is revealed. It approaches a broad-leafed tree. The bird rears up on its robust, muscular hind legs, using its heavy tail as a brace. It stretches its long neck high into the canopy. The massive beak, which we once thought was built to crush bone, is actually a highly efficient nutcracker. It lacks the sharp, downward hook of a raptor. Instead, it is straight and powerful, perfectly adapted to shear through tough vegetation. hard seeds, and fibrous stems. SRC03, Journal article. 2014. We can't tell exactly what specific species of plants Gastornis preferred from this evidence. What it does support is a strictly non-carnivorous diet. The mammals were safe. They did not have to outcompete giant predatory birds to survive. They shared the landscape, quietly occupying the smaller, omnivorous niches while Gastornis browsed the canopy. This realization forces a profound question. If the giant birds weren't eating the mammals, and the apex predator niches in the north were largely empty, what was stopping the mammals from taking over? Why did it take them millions of years to finally get big? We examine a diagram tracking the average body size of mammals from the late Cretaceous through the Paleocene. The line remains almost perfectly flat for millions of years. It hovers at weights below a few kilograms. Mammals survived the KPG extinction precisely because they were small. They required very few calories and could burrow to escape the freezing darkness. But that evolutionary advantage became a strict biological constraint once the world recovered. You cannot evolve a hippo-sized animal from a rat-sized ancestor overnight. It requires tens of thousands of generations of gradual skeletal and metabolic adjustments. The reptiles, having mid-sized survivors like Bretesuchus, had a head start in the race to scale up. The mammals had to build their giants from scratch. And when they finally did, the results were bizarre. Late Paleocene, about 56 million years ago, reconstruction, deep in a swampy North American wetland. The first true mammalian heavyweight pushes through the reeds. This is Barylambda. It is a pantodont, one of the earliest groups of large placental mammals to appear after the extinction. It weighs about 400 kilograms. Roughly the mass of a large modern grizzly bear. But it looks nothing like a bear. Its body is an experimental mashup of traits. It has a long, low skull with a wide muzzle. Its arms are massive, with huge elbow joints ending in broad, flat feet. Barylambda pauses to feed. It rears back on its heavy, muscular hind legs, dropping its weight onto a thick, incredibly robust tail. It forms a stable, three-point tripod stance, much like a giant ground sloth or a gorilla. With its hands free, it pulls high branches down to its mouth, grinding the soft vegetation with high-crowned molars. Evolution has found a functional design for a large herbivore, but the blueprint is raw. SRC06, Journal article. 2022. Present-day, museum collections. To understand just how chaotic this evolutionary phase was, we open a drawer in a natural history museum. Inside rests the skull of another Paleocene mammal, Arctosian. We take a pair of steel calipers and measure the jaw. Arctosian is roughly the size of a medium dog. But its anatomy is a nightmare of contradictions. We measure a massive gap in the upper jaw, a diastema, built specifically to accommodate a pair of lower canine teeth that are so huge they look like tusks. This is the dental weaponry of a dedicated killer. But when we look at the cheek teeth, the narrative collapses. The premolars and molars are not the sharp, shearing blades of a carnivore. They are blunt, rounded, and built for grinding. The skeleton tells a similarly confused story. Arctosian had a long, flexible back and walked flat-footed like a bear. But it possessed the curved claws of a climber. Present-day, phylogenetic models. We look at a diagram of the mammalian family tree. Paleontologists attempt to trace the lineage of Arctosian backward from modern animals. For decades, researchers tried to force animals like Arctosian and Barylambda into neat, recognizable categories. They threw them into wastebasket taxa abroad. Artificial groups like creodonts and condylarths. They assumed they must be the direct ancestors of modern wolves, bears, or hooved animals, but as the fossil record grows, the phylogenetic tree fractures. The lines connecting Arctosian to modern groups turn into dotted, unresolved question marks. One study suggests that these animals share distant ancestry with pangolins. Others argue they are entirely dead-end branches. They are chimeras. They represent a phase of wild, unconstrained experimentation where evolution was blindly throwing traits at the wall to see what survived. SRC06, Journal article. 2022, Late Paleocene, about 56 million years ago, reconstruction, Arctesian moves through the underbrush. A bear dog chimera perfectly adapted to a world without rules. It is a generalist omnivore. It uses its massive canines to scavenge carcasses or take down small prey. Then it shifts to its flat molars to grind roots and fallen fruit. It rules the forest floor not through specialized dominance, but through sheer, rugged adaptability. We can't tell the exact modern descendants of Arctesian from this evidence. What it does support is a highly adaptable, experimental omnivore that thrived in the ecological vacuum. The Paleocene was not a steady, organized march toward the animals we know today. It was a chaotic proving ground. But this era of evolutionary freedom is about to end. The global climate, already sweltering, is preparing to break. The ultimate environmental squeeze is coming. We look at a line graph tracking global temperatures across the boundary between the Paleocene and the Eocene epochs. Roughly 55 million years ago. For millions of years, the line holds steady in the high, warm range of the greenhouse world. But then, it spikes violently upward. This vertical jump represents the Paleocene-Eocene thermal maximum, or PETM. It is one of the most extreme and rapid global warming events in Earth's history. The trigger lies deep underwater. Massive deposits of methane hydrates, previously frozen in the sediments of the ocean floor, destabilize. As the oceans warm, these hydrates melt, releasing billions of tons of carbon into the atmosphere in a geologic blink of an eye. Global temperatures surge by an additional 5 to 8 degrees Celsius. Early Eocene, about 55 million years ago. Reconstruction, the chimera mammals and the giant reptiles face an agonizing environmental squeeze. The heat is oppressive. Dense, hyperhumid tropical forests push out from the equator, marching all the way to the polar regions. The oceans acidify, wiping out fragile deep-sea ecosystems. The evolutionary playground of the Paleocene is over. The PETM acts as a second, brutal filter. It ruthlessly culls the bizarre experimental body plans that cannot adapt to the sudden thermal shock. Yet, amid the terrestrial chaos, the marine realm begins to stabilize. Present-day, fossil recovery. A paleontologist walks along a dredged, sandy beach in the Netherlands. They scan the ground, looking for anomalies among the broken shells and gravel. They bend down and pick up a single, large triangle of fossilized enamel. It is a shark tooth, perfectly preserved, measuring nearly 10 centimeters from root to crown. Similar teeth, recovered from the phosphate beds of Morocco to the riverbanks of Alabama, tell a story of oceanic recovery. We examine the tooth closely. The edges are completely smooth. They lack the fine, saw-like serrations found on the teeth of modern great whites or the later, colossal megalodon. This smooth edge is the signature of a primitive, yet highly successful, lineage of giant sharks. SRC07, Journal article. 2014, Early Eocene, about 55 million years ago. Reconstruction, a massive shadow glides through the warm, shallow seas covering what is now the southern United States. This is Otodus obliquus, reaching estimated lengths of around 10 meters, roughly the size of a modern city bus. It is the first true giant to reclaim the apex predator role in the ocean since the extinction of the marine reptiles. Otodus obliquus patrols the coastal waters. It is a sleek, torpedo-like hunter built for short, devastating bursts of speed. Its massive, smooth-edged teeth are designed to puncture and hold, rather than slice. It hunts large bony fish, smaller sharks, and perhaps the very first, semi-aquatic ancestors of whales that are just beginning to test the waters. Nature is finally restoring the balance of the oceans. SRC07, Journal article. 2014, Early Eocene, Elasmobranch Evolution. We trace the lineage of Otodus obliquus on a phylogenetic diagram. It is not an evolutionary dead end like the chimeras on land. It is a foundational blueprint. Over the next tens of millions of years, the descendants of Otodus will slowly evolve serrated edges on their teeth, eventually giving rise to the largest predatory shark in history, Megalodon. We can't tell the exact trigger of the pattern from this evidence. What it does support is a massive, rapid release of carbon that forced a global ecological reset. The extreme heat of the early Eocene burned away the bizarre experiments of the Paleocene. The animals that survive this thermal gauntlet are no longer unconstrained chimeras. They are highly specialized, highly efficient machines. As the Eocene stabilizes, the shapes of the modern world finally begin to lock into place. Middle Eocene, about 48 million years ago, reconstruction, deep in the Eocene forests of what is now Germany. A dark, tranquil lake sits surrounded by dense, tropical vegetation. The water is perfectly still, reflecting the thick canopy above. But this lake is a death trap. It is a volcanic crater. The bottom waters are completely devoid of oxygen, making decomposition incredibly slow. Periodically, the lake exhales invisible clouds of toxic volcanic gas. Any bird, insect, or mammal flying too low over the water risks suffocation, dropping silently into the anoxic depths below. This lethal environment creates one of the most perfect fossil traps in the world, the mesoil pit. Present-day, mesoil pit preparation. In a specialized preparation lab, a technician works with a dark, damp slab of oil shale recovered from the mesoil site. The shale is notoriously fragile. The moment it is exposed to the air, it begins to dry, crack, and disintegrate, threatening to destroy the delicate fossils trapped inside. To save the specimen, the technician must perform a precise transfer technique, using a fine metal trowel. They carefully expose the surface of the fossil. Working quickly, they mix a batch of clear, liquid epoxy resin and pour it directly over the bone. The resin seeps into the microscopic crevices, locking the fossil in a hard, transparent shell. Once the resin cures, the technician flips the block over and painstakingly scrapes away the original shale backing. The fossil is fully transferred, preserved forever in the artificial amber. Middle Eocene, about 48 million years ago. Reconstruction, the resin transfer reveals a masterpiece of evolutionary design. The fossil belongs to Paleochiropteryx, one of the earliest known bats. It is tiny, with a wingspan under 30 centimeters. But it is not a primitive, experimental chimera. It is a highly specialized, locked-in form. The fossil is so perfectly preserved that we can see the soft tissue. The delicate wing membranes stretch between elongated finger bones. A dark halo surrounding the skeleton reveals the chemical remnants of its original brown fur. Most importantly, the preservation allows us to examine the microscopic structures of the inner ear. The cochlea is massively enlarged, confirming that Paleochiropteryx was already fully capable of echolocation. It could navigate the dark Eocene forests and hunt moths using sound. Exactly like the bats of today. Middle Eocene, modern lineages. We look at a final diagram mapping the survivors of the Eocene. The bizarre, lumbering pantodonts like Barrelamdu are gone. The confusing, bear-dog hybrids like Arctosian have vanished. The giant, terrestrial crocodilians and the massive, bus-sized snakes have retreated or died out as the global greenhouse slowly begins to cool. In their place, the modern lineages have taken root. True carnivores, the ancestors of cats and dogs, have claimed the hunting niches. Hooved mammals have specialized into fleet-footed runners and massive grazers. And in the oceans, the early whales have completely severed their ties to the land, committing to a fully aquatic life alongside the descendants of Otodus. Middle Eocene, about 48 million years ago. Reconstruction. Paleochiropteryx starts through the thick Eocene canopy, a blur of fur and membrane. It snatches an insect from the air and vanishes into the night. We can't tell the exact skin color of Paleochiropteryx from this evidence. What it does support is the presence of fur and intact echolocating ear structures that prove the bat blueprint was already perfected. The 25 million years following the Chicxulub impact were an era of terrifying, beautiful chaos. The destruction of the dinosaurs did not immediately hand the Earth over to the mammals we know today. It created a vacuum. It invited an age of chimeras and monsters. An evolutionary proving ground where life tested every possible shape to survive in a warming world. But as the climate stabilized, the experiments ended. The bizarre forms faded away, leaving behind the sleek, highly specialized blueprints that would eventually conquer the planet. From the ashes of the dinosaurs, the modern world was finally born.